Great. So our third and final speaker is Annie, who will talk about optimal and myopic information acquisition.
All right, so this is joint work with Xiaosheng and Vasilis Syrgkanis. Funny story, this was actually supposed to be presented by Xiaosheng. So after 4 flight delays yesterday, there was finally a cancellation, so I'm going to be here presenting it instead. I apologize in advance, you're going to get my last-minute version instead of him. But I'm nevertheless excited to be telling you about our paper. All right, so we look at a classic setting, which is a decision maker who is repeatedly acquiring information and also taking actions, where his payoff depends on the actions that he takes, and additionally a payoff relevant state that he does not know. Okay, so you can think about a citizen, for example, who's reading news articles to learn about the effectiveness of a policy, and he's also potentially making decisions about whether to protest this policy along the way. Okay, so on top of this classic framework, we consider 2 additional features. Okay, so the first additional feature we consider is acquisition of information from many different sources, which are flexibly correlated. Okay, so you might imagine that 2 liberal news sites or 2 conservative news sites actually provide information that's quite similar on the policy. Okay, the second feature we add is limited attention. So this decision maker can acquire a fixed number of observations each period. You can think about that as the citizen reading perhaps 5 news articles every day. Right, now, what's tricky about this problem is that when you're thinking about what kind of information to acquire, you should be thinking not just about how this information builds on what you already know. You should also be thinking about how this information might be used in the future and how it might combine with future information acquisitions. Right, so let's actually just put that aside for a moment. One strategy that is always available to the decision maker is to act as if today is the last period, okay, and to acquire information in that way. So you can think about this as a myopic or as a greedy strategy. And our main result is that in a canonical setting, okay, where these information sources provide jointly normal signals, it turns out that this myopic rule is sometimes actually the best you can do. So let me clarify what I mean by that. Right, so first, we show that if these signals are acquired in sufficiently large batches every period, so you're reading sufficiently many news articles, then this myopic rule is exactly optimal. Okay. Then we show that for all block sizes, so this would include acquisition of just 1 signal per period, there's a class of environments, which we'll call separable, in which this myopic rule is again exactly optimal. And then in generic environments, this myopic rule eventually becomes optimal at late periods. Right. These results hold across all payoff functions. And in particular, that means it's going to be independent of discounting. Right, so just 2 quick implications of these results. Right, so dynamically optimal solutions tend to be difficult to characterize in models like this, so neighboring models. Often we get implicit characterizations, or instead of going for the optimal solution, we go for a solution that maybe approximates the optimal payoffs. So what we have here is a setting in which the dynamically optimal solution can not only be exactly characterized, but it's actually quite simple to characterize it because you just need to run the greedy algorithm. Okay, so we're hoping that that means that this setting is tractable enough for use in other domains. Okay, the second implication is exactly because these results hold across all payoff functions, what this means is that the myopic rule is actually robust to uncertainty about the payoff function and the timing of decision. All right, so all of you are here today listening about different papers on information acquisition. Why are you here? Maybe you don't know exactly how you're going to use this information down the line, but there's some decision problem you might face at some point in time where something you hear today might be useful. In general, this kind of uncertainty and ambiguity is very difficult to model and solve. But here's a domain where, in fact, the greedy algorithm is, again, going to give you these robust guarantees. All right, so without further ado, here's the model. We have k unknown states. That's theta 1 through theta k. These are fixed over time and jointly normal. Okay, time is discrete. Okay, there's n available signals. Each signal is modeled as a linear combination of the unknown states plus an independent Gaussian noise term. Okay, so these noise terms are independent across time. We're going to assume that the coefficient vectors are known and also the signal variances are known. Okay. each period, the decision maker is going to sample B signals. Okay, so he has B signals to allocate across the n different sources. And he's also going to choose an action. And his payoff is an arbitrary function of these actions, and additionally, a payoff relevant state. Okay, so for now, let me just take that payoff relevant state to be theta 1. I'm going to comment further on this in a moment. Right, so this payoff domain is actually quite general. So it accommodates both of these cases. So one case is an exogenous final date. So here you might imagine the decision maker is actually just going to take one decision, but the decision is going to arrive at an unknown time. Right, another possibility is endogenous stopping with per period costs. So here we can take each action AT to specify both a decision of whether to stop gathering information, and then additionally the action to be taken if stopped. And then you can think of the payoffs as taking the above form, only now T is not a random, exogenously determined time period. It's going to be an endogenously chosen time period. All right, so I wanted to point out a couple of assumptions that we're making in the model. Okay, so one restriction that we're imposing is that the payoff relevant state is one-dimensional. And previously I called that theta 1. It's not so important that it's one of our K states. It can be any linear combination of these unknown states. Okay, the other crucial assumption we're imposing is that the decision maker does not receive any feedback from his actions. So the only way in which he can learn is by acquiring information from these n sources. Okay, we additionally impose an assumption of non-redundancy on the environment. Okay, this assumption says that infinite observations of the available signals is both necessary and also sufficient to fully learn the payoff relevant unknown state. Okay, so you can think about it as an informational environment that is, in a sense, exactly identified. All right, so a strategy is going to consist of two parts. There's going to be an information acquisition strategy, which specifies for every history which block of signals you want to acquire. Okay, there's also a decision strategy, which specifies for every history the action that you want to take. And our paper is really about this information acquisition strategy part of it. All right. I'm going to say that an information acquisition strategy is myopic if at every history it prescribes choosing the B signals that maximally reduce your uncertainty about the payoff relevant state. Now, it's clear that this is a myopic strategy in the sense that you're not thinking about the future. Why is it myopically optimal? So in this normal setting, it turns out that the signals that maximally reduce posterior variance about the payoff relevant state actually Blackwell dominate any other potential sets of signals that you could acquire. So what that means is that it's actually best across all possible payoff criteria. Okay, so that gives us that this information acquisition strategy is optimal if, in fact, the current period were to be the last chance for information acquisition. And correspondingly, I'm going to refer to this as the myopic rule. So here's our first main result. It says that for any informational environment, if B, the number of signals you're acquiring each period, is sufficiently large, then there is an optimal strategy that acquires information myopically, meaning it goes exactly like this. Right, so again, this means that the dynamically optimal strategy is exactly characterizable using this greedy algorithm of just asking which B signals are best next. All right. So suppose you don't like this condition that we're requiring B to be potentially large. Okay, so now I'm going to give you a result that holds for every block size. Say that an informational environment is separable if the variance function can be rewritten in this following way. Okay, so here the variance function is a function on counts. So Qi is the number of times each signal I has been observed. And we're decomposing it in this form here, where what's important is that the number of times the different signals have been observed can be separated in this form. Okay, so here G1 through Gk are convex functions, and then f is a strictly increasing function that's going to be applied over all of these. Now, if the informational environment is separable, then it turns out that for every block size B, the optimal strategy is, again, myopic or greedy. Okay, and that's kind of an abstract definition, so here are just a few examples of separable environments. So one case is an environment with multiple different biases. So say that what you care about learning is X, and you have access to some signal x plus b1 plus b2. Okay. Additionally, you have other signals that inform you about the different biases. Okay, so a graduate student goes to his advisor and asks, how good is my paper? So x is maybe some latent quality of the paper. B1 is, maybe this advisor is nice and he always says nice things. B2 is maybe this advisor hates the topic that the student has picked, so he's always going to bias downwards. And the student can go to other students to find out whether the advisor always inflates or whether he hates this topic. And what is the optimal path of signal acquisition. So that's a separable environment where, again, the greedy algorithm is optimal. Here's another environment. You can imagine sort of a hierarchy of biases. So here the first signal is x plus this bias b1. The second signal is a biased signal about the bias, and you can imagine just stacking these up. This is, again, separable. And let me just skip this last one. Okay, our final main result says the following. So for generic coefficient matrices C, these are the coefficient vectors that define the different signals, there exists a time t star such that for every batch size B, the decision maker has an optimal strategy that proceeds myopically after t star. Okay, now if you're reading this carefully, technically the result says that the optimal strategy becomes myopic. That's a different statement from saying that the myopic strategy becomes optimal. Both of these, in fact, hold. Okay, and this is just a summary of the results. I'll put it up here for a few seconds. Okay, so I wanted to give you some intuition to why these results hold. And a useful way to think about this is to actually consider a one-shot version of our problem. All right, so suppose that you had some t observations to allocate across the different signals. All right. I'm going to call any allocation of these signals t optimal if it minimizes your posterior variance about the payoff relevant state. Okay, so here this is the variance, again a function of the signal counts. We're restricting the signal counts to sum up to t, and any solution n of t here is t optimal. Okay. Now, one thing to notice about these t optimal division vectors is that they don't have to evolve sequentially. And here's a simple example to show that. Right, so here we have three unknown states. Theta 1 is payoff relevant. X2 and X3, if you look at them, are signals that are complementary, okay, meaning observing one instance of X3 is going to increase the value of observing X2. And it's exactly this complementarity that's going to cause a failure in sequentiality of these t-optimal division vectors. Right, so here it turns out that if you have 4 observations to allocate, the best thing to do is to devote 3 of them to X1, 1 of them to X2, and none to X3. If I give you 1 more observation, okay, the best way to allocate 5 observations is to allocate 4 to X1, 1 to X2, 0 to X3. Notice this transition is in fact sequential. Right? So if you start at n of 4 and I give you 1 more observation, you can achieve n of 5. But here's how you should optimally allocate 6 signals. So instead, you should put 3 to X1, 2 to X2, and 1 to X3. Okay? So the problem here is that if you're given a pair of signals, you would like to give them to X2 and X3, but with just 1 signal, you would like to devote that instead to X1. Right? So n of t here does not evolve sequentially. Now, why do we care? Well, suppose that these division vectors, n of t, could in fact be achieved by sequential sampling. In that case, it turns out that myopic information acquisition will in fact achieve each of these t-optimal division vectors, okay, basically because you can interlace them in this sequential way. And we show that this sampling rule is also best for all payoff criteria. Okay, intuitively, what's going on is if you can achieve the best thing at every single period, then there's no intertemporal trade-offs to take into account. Right? There's no issue of maybe I'll allow for higher uncertainty this period so that I can have lower uncertainty in the future periods. Right? So when this n of t sequence can be achieved by a sequential rule, then we do have that the myopic rule is optimal. Okay, so when will that in fact happen, or will it in fact ever happen? So here, this is an example in which the division vectors are sequential. Okay, this is a setting in which we have an independent signal structure and also an independent prior. And really what you want here is just for the observations to be balanced across the different signals. So a simple sampling procedure here that's going to be optimal is just to go x1, x2, x3, and then x1, x2, x3, and so forth. Okay, so that is achievable by a sequential rule. All right, so now how do these two examples compare to one another? Well, so one useful way to understand the relationship is to rewrite example 1 in a way that closely resembles example 2. Okay, so how do we do that? Let me define a transformed state, tilde theta 1, which is equal to theta 1 minus theta 2. So given that, I can re-express this first signal, x1, as just tilde theta 1 plus a noise term. I can do the same thing for the remaining linear combinations, okay, returning a signal structure that was much like the one we saw in the previous example. Okay, so now we have these three transformed states, and what's payoff relevant is going to be their sum. You know, substantively, these are exactly the same example. I've just found a new basis with which to re-express the available signals. Okay? And now we can compare this re-expressed version of our bad example, where sequentiality fails, with the good example in which sequentiality was satisfied. And the key difference here, you can see everything else is the same. The key difference is that the prior in this bad example is correlated and independent over here. Right. Now, the key observation that's really the core of our analysis is the following. As observations of these three different signals over here accumulate, your beliefs over these three transformed states are actually going to tend towards independence. So you can think about that as the signals are decorrelating over time. So therefore, given sufficient observations, we're going to go from a setting like this to a setting much like our original case. All right, so let me skip the final details on this. So, we're going to get that we have a setting approximately like this one, and we need to do a lot of work to transform that into exact statements. But this decorrelation part is really the key of the analysis. And that part, I want to emphasize also, is not special to normality. It essentially follows from a Bayesian central limit theorem. Okay. Now, one plausible intuition for what's going on is the following. So agents in your model are learning. Given that they're learning, naturally the myopic strategy will, in fact, eventually become optimal. Okay. This intuition is actually, it's a bit confused. It's not that it's right or wrong. It really depends on what you mean by learning. Okay, so as these signal acquisitions accumulate, there's two things that are going on. The first thing that happens is the agent's belief about each of the states becomes more precise. And the second thing that happens is the agent's beliefs over the states decorrelates. Okay, and turns out what really matters is this decorrelation. It's not actually the beliefs about the particular states becoming more precise. All right, and in fact, we show that decorrelation is quicker when the prior is less correlated, and also when the prior is less accurate. All right, so just to conclude, we've considered a model of optimal dynamic information acquisition in a fairly standard setting, a canonical setting with normal signals, and we're allowing for flexible correlation across these signals. Now, the presence of potential complementarities and substitutions across these signals generates an intertemporal trade-off. But we show that under certain conditions, these complementarities eventually vanish, and that allows for the myopic strategy to become optimal eventually. Okay, then we also show that when signals are acquired in large batches, we get this optimality immediately. Okay, and then finally in the paper, we look at a few more things, including an extension to multi-agent games. All right, thank you very much. Yeah.
I have two questions.
Okay.
First one is, it might be the last one, is do the results still hold of the optimality of myopic information acquisition when you get additional information about the signals when you take your action at each time step?
So you have in mind a case with free information?
Like every time you take an action, you get some information about the but the information you get depends on the action you take.
So that's the key. So if the information is just free information that's coming in, that's fine. If the information depends on the action that you take, then that's not something we can accommodate.
I see. Is
Yeah.
it like clearly not true, or is it possible?
I would suspect it's not true, but it's not something we've looked at in great detail. Yeah.
And the other question is, do your results say anything about how you should use the information you acquire, like how to use the information you get to take your actions?
Yeah, so again, the focus of this paper is on the information acquisition part of it, but one implication is the following. So in general, if you're solving a problem where you're looking at these decision makers both acquiring information and taking actions, you would have to solve jointly for the information acquisition strategy and also the decision strategy. And one implication of our results is that you can actually separate these two problems in our given domain. Okay, so you can basically cut out the information acquisition part and just suppose that information is flowing in exogenously according to this greedy rule. And then given that, it's much easier to characterize the decision strategy. But that would depend on specifics, like the payoff function and so forth.
Okay, we are a little bit over time, so let's take more questions offline. And let's thank all the speakers again, and see you later.